Hi, welcome to my presentation on measuring information leakage in non-stochastic brute force guessing for ITW 2020. My name is Farhad and I'm from the University of Melbourne, and this paper is in collaboration with Ding, and she's from the University of Melbourne as well. And let's start with the motivation and a summary of what we have done in this paper. So motivation, we are looking at a case that we want to release some information about X, but this X is related to something that we want to keep private U. So how we process X to construct Y is the topic of this paper, so that Y can't be used by the public, particularly an adversarial agent, to be able to construct an estimate of the U, denoted here by U hat. So we want this task of constructing estimate of the U to be very hard. We want to be able to release this Y that people would not be able to guess U, while there is a bit of value in the amount of information that we want to release in X that are not part of the that are not related to the U that we want to release to the general public. So we are thinking of it as a guessing adversary. This adversary looks at Y and tries to guesses or estimates U, and we want to make this job as difficult as possible, of course within the context of the non-stochastic guessing framework, which is the topic of this paper. So in the stochastic case, the one-off guessing has been used before, and people have used in the ratio of the conditional distribution with the prior as a notion of data privacy and information leakage. And in the one-off guessing, your best estimation rule is a maximum a posteriori estimator, and in that case you can construct the maximal leakage and the more general version, the alpha leakage, for the case that your adversary has only one shot in guessing correctly, and you want to understand the probability of that correct guess. Now if you look at the brute force guessing, in there you kind of can do multiple guesses until you land on the correct answer. So imagine if an hacker he wants to see what's your password, he can put different passwords until he gets the correct password and gets into the system. So there you would want to understand how many tries does this adversary needs to do to be able to land on the correct guess, and you want to make that number of tries as large as possible to be able to have your privacy against this brute force guessing adversary. So in that case, in the stochastic case, people look at the prior and posterior guessing entropy and the difference of them as the your measure of information leakage. In this paper, we want to look at an extension of this case to the non-stochastic framework. Okay. Now, why are we looking at the non-stochastic framework? Because in a lot of cases, we might not know the distribution and the probability in advance. We might only have a small data set, so we'd not be able to construct the statistics of the data sets to be able to use them as proxy for the original probability distribution. Or we want to overall even have a way of constructing outputs that not based on randomization, because randomization is not allowed in the policies that we are using for releasing information, and that could be quite a lot of cases when we are dealing with finance, because people don't want to add noise to some information that might be used in an incorrect way. So in this work, we use the original frameworks in brute force guessing. We're trying to extend it to non-stochastic guessing, construct this information leakage based on brute force non-stochastic guessing, and then find this LS star, which is like a maximal information leakage, which is we don't know what even the adversary wants to guess. That's uncertain variable the adversary wants to guess. Now we are quite interested in understanding the relationship between this maximal leakage, the maximal non-stochastic leakage, with the non-stochastic identifiability, which is a notion of privacy in the non-stochastic privacy literature, and the stochastic maximal leakage, which is something that's used quite frequently in the literature for understanding private information leakage. Now let's start with the non-stochastic information leakage measures, and for that we need to have a few notions from the non-stochastic information theory present. Now, the first important thing that we need to understand is the uncertain variables. Uncertain variables are the corresponding to the random variables, but in the non-stochastic case. They are very similar to random variables. The difference is that they don't have any measures or distributions imposed on them. So you would have the set of your samples, your sample space, capital omega, and all the elements of it, the lowercase omega, are your samples. and your uncertain variable is a mapping from that sample space to another space, and the values of that, mapping calculated for lowercase omegas for all your samples would give you the realizations of that uncertain variable, okay? Now in this case, because we don't have any distributions, all the properties of the uncertain variables are captured in the ranges, i.e. all the possible realizations that might come across when you change all, when you select all the samples in the sample space. So you look at all the realizations and that would give you the range, okay? So that range of uncertain variables are very important. Now you can even have conditioning in the uncertain variable word, and there you would deal with the conditioned ranges, okay? So you look at, say, we have a random variable, an uncertain variable y, and I know the realization of that uncertain variable is equal to lowercase y, okay? So in that case, I look at all the samples in the sample space that are compatible with that observation about, uncertain variable y, and say, let's look at the realization of x for only those samples, and that will give me the condition y. So I have this, point in the range of y. I construct the inverse map for construct the y inverse for particularly calculated at that value of y that I know that has been realized, and then I propagate that map through the uncertain variable x and construct this conditional range. Okay, so that's my conditional ranges that I need to keep track when I'm getting access to more information. Now, an important notion when working with uncertain variables in unrelatedness. This is similar to independence for the random variable case, okay? So in the unrelated case, we don't want the range of an uncertain variable to change if we have access to a realization of another uncertain variable, okay? So in that case, we said x and y are unrelated. If knowing y would not change our perception of x, okay? Similarly, we can define conditioned unrelatedness. So we say that, x and y are unrelated condition on z if, again, our perception of the x would not change with and without access to y, okay? So we only take away access to y. We keep z here on the other side when we are conditioning, okay? And then we can have the same as the random variables, a Markov property, but here the uncertain Markov property is that, you have a Markov chain between x, z, and y, if x and y are unrelated given z. So if you were to know z, it doesn't matter what was the realization of x. It wouldn't add any extra information to it. Now, let's get to the guessing and understand non-stochastic guessing leakage, okay? So assume that we are interested, adversary interested in understanding what is the realization of uncertain variable u here, okay, while having access to the realization of y. So if the adversary were to guess what was the realization of y without knowing realization of u without knowing y, it need to make at most this number of guesses, okay? So the number of guesses would be the size of the range of u. You're guessing one by one and going ahead until you get to the correct case, and the worst case is that you have to go to the end, and then that would be the correct guess, okay? So that would be the worst case when you don't know y, and if you know y, you look at the conditional range and then take a size of that, and you need that many guesses, okay? And the ratio of them means how much difference is about your uncertainty about realizations of u when you don't have access to y and when you have access to y. And you look at the worst case here. So, okay, look at the realization of y that makes this ratio as large as possible. That's the realization that leaks the most amount of information about you, okay? So that would be, your non-stochastic guessing leakage. Now, this non-stochastic guessing leakage is interesting because, first of all, it's positive, or it's non-negative, and it could be 0 only if, your u and y are unrelated. So if u and y are unrelated, there is no leakage. Now, there is a nice relationship between the stochastic and non-stochastic guessing leakage here. And if we were to have this uniform distribution and we were to assume that everything is random and the distribution on u is uniform, then the leakage that I have defined here would be the same as the difference of the guessing entropy of the u and the u given that I have access to y, okay? And that's again expected over y. And again, I need this conditional distribution to be uniform too, okay? So and then this difference would end up being equal to the leakage that I've defined here. Okay, so what about the maximal leakage? What will happen if we don't know what's the target of the guessing game that the adversary is running? We don't know what u is. We only have x, and we know that this u is a function of the x. So there is a function g that maps the x to u, and we don't know what this function is. We don't know what u is. The only thing that we know is that, you know, we want to compute is the worst case leakage. Okay. So say for every possible u, that the u, x, and y construct is, you know, Markov chain. So knowing x, the u and y are unrelated. We construct this, you know, leakage from u to y, and then take a supreme over the u's, and that will give me the most amount of information leaked for this u's, okay? Not knowing what u is. So I'll look at the most sensitive case. Now again, you can show that this maximum leakage is non-negative, and it's upper bounded by the zero order entropy, Rainy entropy, which is equal to the logarithm of the range of the x, size of the range of the x. And this conditional, this maximal leakage is zero if and only if the x and y are unrelated, which is again in a very neat property, okay? And if we were to not change x when we are releasing it, so we don't worry about information leakage, or we don't do any kind of treatment when we are releasing, you know, x to the public, the amount of L star, the maximal non-stochastic brute force guessing leakage, is equal to the largest value that it can take, which is the, you know, the zero or the Rainy entropy. And interestingly, we have a post-processing property, which is, you know, if I post-process y to get another uncertain variable z, the amount of leakage that the y that z has, so amount of leakage about x given z, is smaller than the amount of leakage of x from y. Okay, so post-processing reduces the amount of leaked information. You also have additivity. If you have a bunch of unrelated, you know, uncertain variables xi and yi, and you put them together as a bundle, amount of information leaked about 1 to n of all these x's based on access to y 1 to n is the sum of those leakages. Okay, so if you're answering a lot of different queries on different unrelated data sets, the amount of leakages gets summed up together. Okay, in the worst case, in this maximal leakage case. Now, what is the maximal leakage? Can I compute it explicitly? The answer is yes, you can compute maximal leakage in this non-stochastic framework explicitly by this, you know, equation that's shown you here. And the interpretation and the proof of this is essentially showing that, you know, constructing this worst case attribute by looking at how much this range of x changes when you give access to the y, and looking at, you know, the smallest of these ranges, and therefore that smallest range, all the x's that are compatible, we say, you know, we have this u star, which is, you know, a secondary alphabet that we add, and then that would be the value of g of x for those x's, and for all the other x's it would be the actual x, and we say, you know, if this u is equal to g of x, then we're constructing, you know, this would be the worst case attribute, and for that worst case attribute, this is the amount of information that gets leaked. Okay, so it's quite neat because we can explicitly compute what is the amount of information leaked. Now let's get to the, you know, understanding the relationship of what we have defined here in this paper with the other measures of privacy that are already existing in the literature. Okay, one is non-stochastic identifiability. Okay, so if we pick up the stochastic identifiability in this paper from 2016 and extend the non-stochastic case, so if we forget about the distributions and only worry about the ranges, we say that, you know, the map between x and y is epsilon identifiable if the range of x, the size of it divided by the size of the range of x given access to the realizations of the y, this size is upper bounded by epsilon. Okay, so if we were able to meet that, and we can show that this is possible to be achieved by you know, quantizing x. So if you were to quantize x to construct y, then you can achieve this. Then you can say that, you know, so you have this epsilon identifiability. So another way of writing epsilon identifiability is, of course, using it this way. And the interesting thing is that if I have epsilon identifiability, okay, the amount of the maximal information leakage, the maximum information leakage is upper bounded by this, okay? So if I were to make epsilon smaller and smaller, the amount of leaked information gets smaller and smaller. When I increase epsilon, the amount of leaked information increases too, okay? So there is a very nice relationship between this epsilon in the epsilon identifiability and the maximum information leakage, which is quite neat, okay? Now let's say what will happen in the non-stochastic case if I only have one-shot guesses. It's non-stochastic, one-shot guess, and the success is defined here if the adversary would be able to guess correctly with the first go, okay? So here we are not dealing with the probabilities of success. We're constructing, we are investigating cases of this uncertain variables u that the adversary would be able to, correctly guess what was the realization of that u given access, that they have, sorry, this should be lowercase y. Given access that they had the realization of the y was, lowercase y for all the possible ways, okay? So that's, our one guess only case in the non-stochastic framework. So in this case, you can show that actually, if you were to pick up this, L, which was, the amount of leaked information, sorry, this should be, and look at U to Y of this, and take supremum over all the possible U's, but not every U, all the U's that the adversary would be able to correctly guess the realization of U given the realization of Y, okay? So you're having extra constraint here. So before you didn't have that, now you have this extra constraint here. You look at the maximum leakage in this case. This is, of course, smaller than the maximum leakage that we defined because the maximum leakage is over a larger set of U's. The U's don't need to necessarily meet this condition. Now, so this supremum would be equal to I star, okay? Now, what is I star? I star is the maximin information, a notion of information in the non-stochastic information theory literature. And it's related to the the gas corner common information. When you don't worry about the probabilities anymore, you take a supremum over them, and it has been shown in the past to be quite intimately related to the zero error capacity in a work in 2013 in the non-stochastic framework, and in the stochastic framework in a work by Wolf and co-author in 2004. Okay, and also in another paper by myself and co-author. Another co-author in this ITW, which if you want you can get to see it, we can show that this I star is highly related to it's intimately related to this common uncertain variable. So if you were to pick up the notion of common random variable, for instance gas corner, and then drop the probabilities as I've said above, in the maximal gas corner common information, you can construct common uncertain variables, and the entropy of the zero entropy of that, zero Rayleigh entropy of that would give you the common uncertain variable is, and zero entropy would give you the I star, okay? So this gives a very nice relationship between L star and I star 2, which you might be able to use maybe for bounding, zero capacity, if that's what you're interested in, not privacy. Okay, what about the stochastic case? If you pick up the maximal leakage, the stochastic maximal leakage, and look at, the ratio of the probabilities, how much the probabilities change, instead of looking at the ratio of how much the size of the range changes, so we're going to a stochastic case, we're looking at probabilities, not the ranges only, then we would end up, with this L tilde, which is the original maximum leakage, and you can show that, our L star, which is the maximal non-stochastic leakage, is upper bounded by the supremum of this stochastic leakage over all the conditional probabilities. Okay, so it's like you're dropping away the probability plus an extra term. Okay, so this bound is a little bit loose. One of our future work would be to tighten this bound a little bit and hopefully drop this extra term. That would mean that the worst case for probabilities would give you the worst case non-stochastic leakage. So that would be the result of the paper. Now to conclude, I just wanted to mention that the aim of this paper was to kind of use this brute force guessing framework that are out there and try to tailor it to the non-stochastic framework and construct this maximal leakage based on that, and then try to relate this non-stochastic to the stochastic versions of the information leakage and the non-stochastic information leakages that are already there, like the non-stochastic identifiability and the maximin information. And for future work, certainly And important work, as I said earlier, would be about tightening this relationship between the stochastic and non-stochastic leakage, and understanding the dynamic privacy with continual observation. So if the observation is coming over time, and you're releasing information over time as well. And with that, I would like to thank you.